Hi there, my name is Ali Begen. I'm a computer science professor at Özyeğin University in Istanbul, Turkey. I've been working on streaming media for about 20 years. Today, I'll be talking one of our recent works on low latency live streaming. A fun fact is that in 1969, the live broadcast from the surface of the moon was watched by hundreds of millions of people, and the latency they had was about 3 seconds. 50 years later, the Super Bowl 53, it was also streamed by millions, but in that case, the latency was more than 45 seconds. Yet low latency has seen a lot of developments in terms of implementation and standardization in the last few years. So we are in a much better position than we were a couple of years ago. One of the main drivers for low latency is live sports. We are witnessing streaming providers signing on multi-billion-dollar contracts for streaming rights of the football and soccer games around the world. And they certainly know that to earn that money back, they must offer a superb video experience. HD or even 4K resolution, high frame rate, high dynamic range, multi-channel audio are all in high demand when it comes to premium sports streaming. However, one of the most important factors that affect the viewer experience is how smooth the video playback is. Stalls are sometimes inevitable due to the uncertainty of IP networking, and since we use very small buffers for low latency live streaming, the odds are higher for us to stall for longer and more frequently. Let's look at this video. Messi is kicking a penalty kick and millions are watching live. And oops, the video froze. Was it a goal or did the goalkeeper save it? Well, a few seconds later, the video resumes. Okay, it was a goal. I guess we can all agree that this is quite irritating, especially when we are watching the game with our friends. Now let's look at another example. There's Barcelona against Real Madrid, and Marcelo has the ball and passes the ball to Ronaldo, right? And he makes quite a shot. Okay, the video froze again, and we don't know whether it was a goal or it was not a goal. Well, when the video resumes, okay, this was a mess. Well, it was really a close mess. Anyway, so this was really an exciting moment in that game because it happened really in the last 10 minutes of the game, and the score at the time was already a draw. So a goal was certainly very important. Now, low latency sports is the main driver for low latency live streaming. And when it comes to offering a premium low latency live streaming service, well, we have a couple of tricks in our toolbox. One of the tricks we have is called adaptive playback. We can slow down the playback speed by changing the frames played per second and doing this the same thing for audio and captions as well, right? If we're about to run out of media in our playback buffer. This slowdown will give us extra time to fetch more data, hoping that we can avoid stalling altogether. For example, if we play a 2-second content in 3 seconds, which means it is 50% slower, we will create an additional buffer of 1 second over the course of 3 seconds. You can imagine, though, we cannot keep doing this unless we also take some counter action to bring the latency down to the initial value or the target value. Now, to do that, we need to increase the playback speed for a brief amount of time. And we can only do that whenever we have extra data in our playback buffer. This adaptive playback idea was adopted from the voice over IP applications, and it was many years ago. And at the time, it really resulted in one of the biggest improvements in audio quality. Now let's look at how we can adjust the playback speed in real time. This is showing a pseudocode for our LOL Plus, Low on Latency Plus implementation that we developed for the Twitch Grand Challenge on this subject a year ago. This was implemented for the public reference implementation, dash.js, and it's already part of the official branch as of version number 4. As you can see from the code, we first check how the current buffer is compared to a minimum safe buffer level. If the buffer is critically low, we don't need to check anything further, and we don't care what the current latency is, and we slow down right away because there's an imminent risk of stalling. The amount of speed reduction depends on how low the buffer is. On the other hand, if the buffer is okay, meaning that it's at least as high as the minimum safe threshold, then we check how the current latency compares to the target latency. Then, based on that, we need to adjust our playback speed if necessary. Here are a couple of examples. So we have some configurable parameters in this code. The safe buffer threshold is half a second in this case. Target latency is 1.5 seconds. And the playback speed is allowed to change by plus minus 30%. So we can slow down by 30% or we can speed up by 30%. In scenario number 1, the buffer level is 0.3 seconds, so it's below the safe buffer value. So in that case, we just need to slow down. We don't care what the latency is, we just need to slow down. In scenario number 2, the buffer is at this minimum safe buffer threshold, so that's okay. But our current latency is a bit lower than the target value, so we are unnecessarily risking our playback. So we can also slow down a bit here to build up a larger buffer, which will give us more protection. And in the third scenario, the buffer is 0.7 seconds, so it's higher than what we minimally need, but the latency is also higher than the current value. So now in this case, we need to accelerate the playback a bit so that we can catch up with the live stream, live edge, right? So looking at some examples here, I'm showing 3 different algorithms in this slide, and we have at the bottom we have the hybrid approach, which is the LOL plus, and in the middle it's the dash.js default algorithm implementation, and then at the top it is the another flavor of playback speed control. Now at the bottom, as you can see, the LOL plus is checking both the buffer level as well as the latency level. So when there is a significant bandwidth drop, obviously we are going to stall. There is no escape from that. But as soon as the bandwidth recovers, we are able to continue streaming, and we better bring the latency down to the target value as soon as possible. As in this case, you can see the stall duration is limited to less than 3 seconds. In the second case, in the middle plot, here we are paying attention to only the current latency. And that's really what dash.js does today. And if the current latency increases, you're going to increase the playback speed, and you're going to try to catch up with the live edge. Now, obviously, we will get a lot more stalls in this case because we are not really checking the buffer. But we indeed have a good control on the target latency. In the last example, at the very top, the same algorithm, but now we are only paying attention to the buffer conditions. So in this case, we have less stalls compared to the middle scenario, but we also have less control on the latency. So overall, looking at all these plots, we understand that doing a hybrid playback speed control is the way to go. Now, is that really the best thing we can do? That's the question we are trying to answer in this study. Now, when the buffer is almost depleted, we really don't have much of a choice, right? We need to slow down so that hopefully we will recover from that transient issue without any stalling. However, if we can plan things better ahead of time, we might pick more appropriate places where we can adjust the playback speed. If the speed change is subtle, nobody will notice it, but subtle speed changes are rarely sufficient in low latency. They don't really provide us much gain in short time skills. In other words, we need fast and aggressive reactions most of the time, and such playback speed changes may be easily noticeable or visible or audible by the viewers. To mitigate this, we better carefully select when we will change the playback speed, right? And by how much. We call this, we have a solution for this, and we call it ContentAware Playback Speed Control. In short, it's written as CAPS. This work was published just a few weeks ago in the ACM Multimedia Systems Conference, so you can go ahead and download the paper if you want to read about this algorithm. Now, ease of implementation and scalability are two important design factors for us in this work. So we start with a simple approach. So let's assume that we have a magical number that corresponds to the importance of a scene, or better said, the sensitivity of that scene to playback speed changes. In this case, we call this magical number event density, and it takes a value between 0 and 1. 1 means the scene is extremely important, meaning that the playback speed changes faster or slower, right, should be avoided at all costs. 0 means the scene is not really that important or insensitive to playback speed changes, so it could be just a static scene, for example, where nobody is talking. So in that case, we can do the playback speed changes as much as we like. In a live content, obviously, we don't know what the event density is a priori, right? So we need to be able to compute this value in real time and convey this information to the client so that it can use that information appropriately. Now, there are a couple of different ways of doing this. Here is the first approach. This is the Inband approach. As the content is being encoded by the live encoder, obviously a lot of details are being computed and known by the encoder itself, right? This could be the amount of motion in a scene, the amount of conversation in the audio, or something else, determined by an advanced AI model. Now, the event density can be generated per frame or per CMF chunk, which could be as small as a single video frame, or it could be a group of frames, right? And we publish this information in the metadata track, timed metadata track. So along with the audio and video and everything else, this is also posted on origin server, and the client just grabs that information, right? And this is a concurrent operation. So as I grab the data from the server, I also grabbed its event density information. Now, CAPS is implemented on top of the existing ABR, so the playback speed controller is somewhat independent from the rate adaptation. Obviously, they have a relationship, but it can be implemented on top of any ABR algorithm, if you like. Now, the other approach is out-of-band signaling, and in this case, we have a third party who is providing some sort of metadata about the game we are watching at low latency. So in this case, the data is coming to our client from a third party, not necessarily part of the workflow itself. And this third-party provider could be just a commentary service, it could be a sports data feeder service, and so on. Based on the incoming data, the client can infer what the real-time event density values are, and subsequently can adjust the playback speed accordingly. In our implementation, we use the former approach, so we use the Inband approach. But this is also a possibility. Now let's look at our modified playback speed control algorithm. So in this case, the algorithm is written a bit differently, but more or less it's doing the same thing, except that now we also have to include the event density, which is denoted by gamma in this case, into account. Now, looking at the equations, what's really happening is that gamma is a dampening factor here. If the event is more important or more sensitive, the less playback speed change we can make. Now let's look at some results we have. In these experiments, the target latency was set to 3 seconds, okay? The safe buffer threshold was set to 1 second. So anything, if we have any data less than 1 second in the playback buffer, that will be a critical value for us. And we let the client change the playback speed by plus minus 30%. This is just a number we picked for this study. It could be plus minus 50%, or it could be a different value in the negative direction than it is for the positive direction. On the top of these two plots, the behavior of the default algorithm in dash.js is shown. The event densities are also overlaid in these plots, so it's a time series plot. On the right y-axis, we have the playback speed, which is shown in red, and on the x-axis, we have the latency and buffer occupancy, which are shown in blue and green respectively, okay? So when the bandwidth drops significantly around 165 seconds, the stalls start happening. I mean, the bandwidth drop is significant, so we are going to have some stalls. And the default algorithm is obviously is only trying to keep the target latency. When there is a stall, the latency will increase. So as soon as there's a chance to increase the playback speed, the default algorithm will try to catch up with the live edge. It doesn't pay attention to the event density. It doesn't pay attention to the buffer level. So increasing this playback speed is the only action it can take. And over time, it can also cause some further stalling, and that's not good, around 215 seconds. On the other hand, the LOL Plus implementation pays attention to both buffer and the latency, if you remember. So it avoids the unnecessary stallings. I mean, there are some stallings which it cannot avoid, but there are other ones that it can easily avoid by adjusting the playback speed carefully. So overall, LOL Plus is providing a way better experience than the default algorithm in this case, especially in terms of stall performance. Now, looking at the comparison between the LOL Plus and the CAPS, well, the differences are subtle, but it is actually important. Now, the main difference is obviously is the event density function. So LOL Plus doesn't pay attention to that, but CAPS uses that information right in the playback speed algorithm. The CAPS knows when the playback speed shouldn't be changed, and it makes every effort to do so. So if the scene is sensitive to playback speed changes, it will try to keep a 1x playback speed so that it respects to the importance of the content at that time. But at the same time, we also need to monitor the buffer conditions and so on. Once the conditions get back to normal, it will take a bit longer time for us to reach the target value for the latency. But I guess it's an acceptable cost for having a better user experience during these more important parts of the content. This is another plot that puts everything together, comparing the three different playback speed controllers, the default algorithm, LOL Plus, and then CAPS. As you can see, the default algorithm cannot go lower than 1x. It only accelerates to catch up with the live edge. LOL Plus can go in either direction, but doesn't pay attention to the importance of the content. And CAPS, on the other hand, tries to respect the event densities over time. We have a website showing a couple of different videos for different traces and so on. All these real-time metrics are also shown on, plotted in real time on the same page. So you can compare different algorithms next to each other and appreciate the improvements by CAPS, or maybe you won't notice, but at least in that case, you can also let us know your feedback. There's a link for this demo website at the end of the presentation. So there are many artistic reasons for using fast and or slow motion video. And this is not really an exact science to figure out how sensitive a scene is to changing playback speeds. Obviously, for sports or for specific types of content, we can develop some models to detect when the content is actually important, so the playback speed changes should be limited or not, right? To generalize this, it's going to be a way more complicated process. Now, for football or soccer for the Americans, we have a number of observations that we can use for such games because we watched a lot of soccer games and we know when things get more important or the viewers pay more attention to the video and so on. So we can try to understand such scenes using that information. For other sports, we can also try to learn from different video sources and then implement them in our code. But to generalize this concept to any video, obviously, it's a very long way before we can do that. Now, obviously, myself and my students are still working on this, so there are a couple of ongoing efforts in this domain. First of all, we are trying to apply this algorithm as an integration to some of the data providers like the ones listed over here. It doesn't matter which one, but we just want to use the real-time gaming data to be able to feed the CAPS algorithm. And then we want to extend this algorithm to other sports, not just soccer, or even non-sports content. And a very useful use case for this type of algorithm will be really to repurpose to support on-demand video, so not necessarily live video. So we will have a lot more time to process the content. But the goal would be we cut off the not so interesting parts of the content so we can actually finish watching the entire content in a much shorter time. So assume that there is a Netflix movie at for 2 hours. If we run this algorithm and then this algorithm knows exactly which scenes will be boring to you so that it can play it faster. If it can do that automatically, maybe you will end up finishing the movie in 1 hour. So you will save a lot of time, right? And then support for streaming content with variable frame rate. This is a difficult problem. There's really not much content out there with variable frame rate, but we expect this will be more and more in the future. So, we should also pay attention to this. As I finish my talk, I am happy to mention that our MMC's paper actually received a couple of awards. First of all, from the conference, it received the Best Domain Industry Paper Award. And then it also received the first position in this year's dash.js Excellence in Dash Awards. So I thank all of my co-authors, my students, and I thank to those who actually voted for our paper. This is a great honor to have received these awards. So this is the QR code for our website for the demo and source code. So get the code, get the test sequences, download it, test it, and then if you find any bugs, let us know. If you like it, let us know. If you don't like it, let us know that too. And what kind of improvements we can make. If you have any ideas, suggestions, please let us know too. Here are our email addresses, and we will be more than happy to answer your questions. Thank you.